is section 8.5, application of matrices and determinants. So in chapter 7, we looked at systems of equations, solving them through substitution and elimination, eventually putting them together into solving systems of equations with matrices and row and reduced or echelon form. One more method that uses determinants to solve systems of equations is Cramer's rule. What I have here is a lot of pretty technical writing, but I'm going to talk through it. So you have a system of equations. A sub 1, A sub 2 are the coefficients on x. B sub 1, B sub 2 are the coefficients on the y's. C sub 1, C sub 2 are the constant values. To find an x solution to this system, you create that fraction. The numerator of that fraction right here is the determinant of a matrix of a 2 by 2 if your A sub 1, A sub 2 values get replaced with C sub 1 and C sub 2 values. The denominator is just the determinant of the coefficient matrix A sub 1, A sub 2, B sub 1, B sub 2. To find the y value, you create the same kind of fraction. The numerator is the determinant if you replace the y column, B sub 1, B sub 2, with the constant column, C sub 1, C sub 2. Then the denominator again, determinant of the coefficient matrix. And this can be generalized if you have a z variable, there's a z column, w variable, a w column, so on. So let's look at a specific example for this, okay? Kind of how you create all of these matrices. So the coefficient matrix, you should remember that from section 1. Just the coefficients from x's and y's. Now to create D is the same as the coefficient matrix. I don't know why there's another name, but there is, so we'll go with it. This blurry kind of thing right here is D sub x. You guessed it, this is D sub y. So to create those, you'll go to the constant column in the system. I didn't mean to do that, meant to do this. Why not? And then the constants are going to go replace. That's a really poor looking arrow. Wow. The constant column is going to replace the coefficients in the x column. So to do that, the y's, of course, are going to stay the same, -5 and 3, but the x column coefficients are going to be replaced with 3 and 8. To create d sub y, same kind of thing. But now, the constants are going to replace the y coefficients. So for d sub y, the x column is the same as the D matrix. But then the y column is your constants, 3 and 8. So D d sub x, d sub y, and of course this could be replicated if there's a z or a w or any other number of variables. So let's look at an example of this. Sample A. We're going to want a D matrix, D sub x, and D sub y. So D, of course, that's just the coefficient matrix. 1, -2, -3, and 3. D sub x, you're going to replace the x column with the constant column. So -11, 12. And then the y column, just cover that down. To create d sub y, x column is going to be the same, but then the y column replaced with your constant column. So now to solve for x, we want the determinant of d sub x over the determinant of d. To solve for y, the determinant of d sub y over the determinant of d. So these are all 2 by 2 matrices, pretty simple to figure out. D sub x, -11 times 3 minus -2 times 24, so -33 minus -24, gonna be -9. And determinant of d, 1 times 3 minus -2 times -3, so 3 minus 6. And we're back. My kid was playing outside. The one thought, hey, there's Dad. Let me go find him, bang his window, make noise, and it all kind of went downhill. So we're back. So -9 over -3 gives you 3. Then repeat that process for solving for y. So the determinant of d sub y. So determinant 1 times 12 minus -11 times -3, so 12 minus 33, going to be -21. Determinant of d, still -3, so we have 7. So putting those together, we get the order pair of 3, 7. Alright, try example B. Check your answer with my completed notes online.